Hello everyone and welcome back to the final two episodes of the electrolysis series. In today's video, we will be talking about rechargeable batteries, and let me just get the color up, and we will look at the recharge process, making reference to overall equation, half equations, oxidizing and reducing agents, polarities of electrodes, and the energy transformation. So all the things that we would look at whenever we analyze any redox process. And specifically, we will also look at the requirements for a cell to be recharged because, as you know, not every cell is rechargeable. So what distinguishes a rechargeable battery from a non-rechargeable one is something that we want to look at today. Okay, so I show you this diagram at the very start of this topic, I think. And this is just a summary again. So when you talk about electrochemical cells, you can have either galvanic cells or electrolytic cells. We looked at these two, fuel cells and primary cells, last term, and we've spent the last 3 weeks talking about electrolytic cell. So today we're going to end the topic with secondary cells. And before we start, there are just two terminologies that I want to make sure you understand. Whenever we talk about secondary cells, there are two processes that it can undergo discharge. Discharge is basically when the cell is producing electricity. So it's when chemical energy is going to electrical energy. So the principles of discharge is going to be the principle of a galvanic cell. And then you have recharge, and there goes my first typo. Recharge is when electrical energy is being converted back to chemical energy. So recharge is the same as charge, which is, for example, when you say I'm charging my phone, you're basically referring to recharge as a process. But the word charge is just a little bit too vague in chemistry. So please don't use charge ever. If you want to describe either of these processes, be more specific, say either discharge or recharge. So recharge would apply to, well, recharge would use all of the principles of an electrolytic cell or the electrolysis, essentially the same. I'm not going to go through this table, but this is just a quick comparison that I made a few years ago for the similarities and differences between primary cells, secondary cells, and fuel cells. I'm not a big fan of the graphic now that I look at it, but I'm just going to leave it here and you can read it on your own, or you can make one yourself and then compare it with this one. This is another graphic that you have seen. I think the original headings were galvanic cells and electrolytic cells, but as I mentioned earlier, since discharge uses all the principles of galvanic cells and recharge uses all the principle of electrolysis, you can have the same graphic and just replace the title with discharge and recharge. So rechargeable batteries are really interesting because they include principles of both galvanic cells and electrolytic cells. And so you need to really know whether you're looking at the discharge cycle or the recharge cycle when you analyze a cell. I'm going to go through one example in this video just to show you how everything works. And the example that I'm going to use is the lead acid cell. So this is a lead acid car battery, definitely a rechargeable battery. Very, very heavy. I'm not even sure, I don't have a car, otherwise I'll go and take a photo of the battery in my car. But the difference between a battery and a cell is a battery is essentially a stack of cells. So the lead acid car battery usually consists of 6 lead acid cells in a stack like so, and then you can has a voltage of around 12. So we're going to look at one cell, one of these. So you have the lead, which is the red electrode, and then you have the lead dioxide, so PbO2, which is the blue. What does it say, green? That's not green. Electrode, and then it's submerged in a solution. The voltage of each of these is around 2.1 volt according to this diagram, and then you have a separator, which is the yellow bit here. So we're just going to look at the operation of one of these cells. All right, let's make the diagram a bit bigger. So there's that. I'm just gonna, do I label separator? Yeah. All right, let's say when I ask you to analyze, suppose that I ask you to analyze a rechargeable battery, the first thing that I will give you is a diagram, and I will tell you, sometimes I don't, but in this particular case, well, and I have to tell you something about this. In this particular case, I probably can say this diagram is a diagram of the cell during discharge. So when you look at the diagram, how do you know whether the cell is undergoing discharge or recharge? And the answer for that is you look at whether the electrodes are being connected to a power supply or not. If they are connected to a power supply, obviously it is recharge. This is not a power supply. This is just a voltmeter, so it's just a way to measure the voltage. And I can put, I can actually delete that. I can put 2.1 volt here as well. Sometimes they don't actually show you this, and they just say it's discharge. And then sometimes you can see like open end on the electrode. It doesn't mean that it's not connected to anything. It just means that they don't show it in that diagram. So this is diagram discharge. There is no power supply being connected to the electrodes. Another thing that I probably will tell you is I'm going to tell you some information about the electrodes. So the cell consists of a lead electrode, we've got that, and a lead dioxide electrode submerged in a solution of H2SO4 electrolyte. So you get an extra piece of information here. You know that the electrolyte is sulfuric acid or H2SO4. That's why it's called lead acid cell anyway. So H2SO4, actually let's put, I think I put H2SO4 somewhere here, but there's H2SO4 being the electrolyte. It's a solution, so it's aqueous. There is a porous separator which separates the cell into two compartments. So this is your separator. Okay, the last thing that I need to give you, if I want you to analyze the cell, is I need to give you some form of equations. In the majority of cases, the half equations and the equations in a real battery is so much more complicated than something that you can find in the electrochemical series. So unlike electrolysis, when you normally have to work out what reaction is taking place yourself, in the case of a rechargeable battery, I would give you either this or two half equations or something like that. So you get the discharge. Also very important that I tell you in the question, or whoever writes the question tells you that this is the equation of discharge. Otherwise, anyway, so that's all the information. Let's say, yeah, that's H2SO4. So if I give you all this information, so this is the diagram of a battery or cell during discharge, and you have the discharge overall equation. What kind of questions can be asked if this information is given? Excuse me. So the same questions that I've asked in electrolytic cells will be asked here. You need to write half equations. Identify cathode and anode, describe the flow of ions. Obviously, there isn't a question asking you what is the purpose of this cell, because hopefully you know that it's a battery, so it just produces electricity during this cycle. So how do we get the half equations from the overall equations? You find oxidation numbers if everything else fails. So going to do that now, so let's just go from left to right. So -2, +4, 0. Do I bother with this? All right, let's do that. -2, +6. This is clearly a spectator ion because it's all about lead. +1, I'm pretty sure I've actually used this example in the past when we just practice writing half equations. Okay, so these are the oxidation numbers of every species. You can see that the interesting thing about this cell is that you get the same product from two different reactions, because the PbO2, the lead in PbO2 has a decrease in oxidation number from +4 to +2. So this one must undergo reduction. And the Pb has an increase in oxidation number from 0 to +2. So it undergoes oxidation. So I'm just going to write the reduction here. So PbO2 going to PbSO4. Let's see how much room I need. Probably quite a bit, actually. PbSO4. So we're going to add the SO4 because you have a spectator ions. If you don't add it, you're not going to be able to balance the equation. And then you can use cohes if you want, because this is acidic, because it's like the lead acid cell. So I'm just going to balance oxygen by adding 2H2O, adding 4H plus, and 4 electrons. Something is wrong, 2 electrons, sorry, because that's already 2 minus. So 2 electrons, which also makes sense because you're going from +4 to +2, so 2 electrons must be added. Do not forget states. You can just copy the state from the overall equation. So that's the half equation for reduction. Now, once you get the reduction one, if you want, you can subtract it from the overall to get the oxidation, which I'm going to do that now because I really can't be bothered. So Pb, because this one's really easy. So 2SO4, 1SO4, so there should be 1SO4, 2 minus here. The 4H plus is used, the water is used, so I just need PbSO4. Notice how there are two PbSO4 in the overall equation, so one must come from reduction and the other from oxidation. And then I just add 2 electrons to balance the electrons. Put in the state. Okay, so half equations for reduction and oxidation. Identify the cathode. So the cathode is side of reduction, which means that the cathode is going to be this one. This is your cathode. So cathode is PbO2 and the anode is Pb. So this is really interesting because in this particular cell, the electrodes actually participate in the reaction, which can happen. And if you recall the old galvanic cells that we analyzed, that happens a lot. It's just it normally doesn't happen in electrolysis, and then when it happens again, people just get weirded out. Describe the flow of ions. The ions in question, I think it's H plus, so it's going to flow to the cathode. So I'm just going to go H plus crosses. There is a separator, so it should be able to go through the separator. So it crosses the separator to flow to cathode. So during discharge, there will be a reduction in the acidity of this acid because hydrogen ions are being used. If I'm very mean, so this is the flow. If I'm very mean, I could ask you something relating to pH, but I don't think I'm allowed to do that these days. Okay, so that's discharge. Well, good. Let's talk about what actually happens to this cell. I think I'm supposed to do one more thing. Yeah, so polarities of electrodes, positive cathode, negative anode. This is discharge, not electrolysis. So the cathode is positive, the anode's negative. All right, what I want to actually talk about is what happened to the electrodes after a while. I explain why this is not here. Is if you look at the half equations, you can see, let's look at that PbSO4 solid is being produced in both, half cells, if you will, or at both electrodes. So the cathode, which is PbO2, is a solid and is actually the reactant. So it is being used up over time to produce PbSO4. Similarly, at the anode, Pb, which is the actual anode or lead, is also participating in the reaction and it is being converted to PbSO4. So I'm just going to use this. It's not highlight, it's like a textile thing. There's so many interesting tools with PowerPoint, by the way. I'm just going to represent PbSO4 with this purple, really disgusting. It looks like a paste, but let's just assume it's solid. And what actually will happen over time is you're going to see a layer of PbSO4 covering the electrode. And one thing that is not shown really clearly here is that the electrodes, the lead and the lead oxide in the electrode would also shrink in size. So you really just have, and then you have PbSO4 covering it. So the good thing about this cell and the very important thing about this cell is that the product, which is PbSO4, I mean, you don't really need to worry too much about water because it's always in the solution. But the product of discharge, which is PbSO4, first of all, is a solid, and second of all, it is able to stick onto the electrodes after it is produced, so it remains in contact with the electrode. So you don't actually have a case when the PbSO4, even if it's a solid, like, just go here. So you don't have something like this. You don't have PbSO4 dropping to the bottom of the cell or getting washed away by the electrolyte, even though obviously in a cell you cannot guarantee that 100% of the PbSO4 or the lead sulfate produced will stick onto the electrode, but the majority of them will, and that's really important because this is the requirement for recharge to occur. The product of discharge has to remain in contact with the electrodes, so that when you actually put the power supply into the electrode, so you connect the electrodes with a power supply, the product, the PbSO4, could actually be converted back to PbO2 and Pb. Without the product of discharge remaining in contact with the electrodes, you cannot have the reverse reaction. So in general, in order for a cell to be recharged, language here is wrong. Okay, the products of discharge must remain in contact with the electrodes in the convertible form. The convertible form just means that it doesn't decompose into something else, so it remains PbSO4. It doesn't suddenly turn into PbO and something. So that's the convertible form. It doesn't decompose. I don't think I've seen a question when it's not in its convertible form, so you don't have to worry too much about that. So let's talk about the actual equations. I think I managed to fit everything in. So discharge, this is the overall equation of discharge. I just rewrote the equation from before. So the overall equation of recharge is just going to be the reverse of that. So the product of discharge now becomes the reactants of recharge. Okay. This is the reduction of discharge earlier, and you're going to reverse this equation. So reduction of discharge reversed to become oxidation of recharge. And similarly, the oxidation of discharge, you're going to have to reverse it, and it's going to become the reduction of recharge. So you have to reverse this equation. A lot of students think that, oh, reduction of discharge is oxidation of recharge. That's not right. You have to reverse the reduction of discharge for it to become the oxidation of recharge. You pretty much have to reverse these equations. That's the rule. But reduction will become oxidation once reversed, and vice versa. So just reverse the equation, okay? I feel like I wasn't speaking English just then. So this is the summary. I'll have a table later, I think. The reduction of discharge is the reverse of the oxidation of recharge, and the oxidation of discharge is the reverse of the reduction of recharge. It sounds a little bit complicated, but if you think about it, it's actually, it's quite easy to understand, I think. So let's go back to here. This is the recharge overall equation. And if this is actually recharge, you need to replace the voltmeter with a power supply. The half equation for reduction is going to be PbSO4 plus 2 electrons going to here, and that's the oxidation. So I just rewrote what I showed you earlier. So if you think about what happened with reduction, electrons are coming, let's use a different, maybe not. Electrons are coming out of here into Pb, because Pb is, electrons are coming out of the power supply, and they are going to be received by the PbSO4, and that is going to reduce the PbSO4 and convert it back into Pb. So this is why the PbSO4 has to remain in contact with the electrode so that it could receive these electrons when the cell is recharged. Similarly, the electrons is gonna get, I say donated is a nice word, it's really just sucked out by force. The electrons from PbSO4 will leave PbSO4 to go into the positive terminal of the power supply. And through that process, PbSO4 will be oxidized back into PbO2. So you're going to have, if you have a 100% success rate when it comes to recharge, you're going to restore the two electrodes, which are the two original reactants, back to their original form. Okay. Probably should delete this because it looks really strange without the PbSO4. I think I've been talking too much. So interesting. It's identify the cathode. The cathode in this case is going to be Pb. So the cathode in the previous case was PbO2, now it's Pb, and the anode is PbO2. The thing is, you probably will not completely discharge Pb and PbO2, so they should still be used as the surface of reduction and oxidation. It's probably a mixture of Pb and PbSO4, but we normally don't refer to the product because it's not there all the time. So you can't just write Pb and PbO2 as the cathode and the anode. The flow of ions. So once again, H plus will go to cathode. H plus crosses the what am I saying? Separator to go to cathode, which is in this case the Pb. So it's going to go in the opposite direction compared to before. It's going to go like that. Okay, so that's recharge. I'll put the arrow in the PowerPoint, the other PowerPoint. Actually, no, I think I can put it in this one. This one will stay. H plus. I don't even know what I'm talking about anymore. Yes, one last thing is to talk about the polarities of the electrodes. Notice how this stays negative and this stays positive throughout the entire process. If we go back a few slides, this is going to take a while. But let's go back. If we go back to this one, so this is discharge, and during discharge, the cathode was PbO2, which is positive, and the anode was Pb, which is negative. And now if you continue, we go through the entire process, again, you will see that even during recharge, the Pb electrode remains negative and the PbO2 electrodes remain positive. The only difference here is that during recharge, Pb has gone from being the anode to the cathode. So Pb was the anode of discharge, it is now the cathode of recharge. PbO2 was the cathode of discharge, it is now the anode of recharge. So the nature of the electrodes have changed, but their polarities, interestingly, actually stay the same throughout the process. A lot of students make this mistake, but keep in mind that the polarities of the electrodes do not change between discharge and recharge. And by polarities, I mean positive or negative. So Pb is always a negative electrode in this cell, regardless of whether you're discharging or recharging, and PbO2 is always the positive electrode. However, what actually changes is the reactions that occur in each electrode. So the anode becomes the cathode, and the cathode becomes the anode, whereas their polarities remain the same. Okay? My old chemistry teacher, when I was in year 12, taught me this, and I've been trying to teach it to everyone. I don't think anyone uses it but me. I don't know why, but the one that he said, this is just a summary of the polarities of electrodes. So red cat and an ox will be true regardless. It's one of the similarities between any redox process. If you look back at one of the diagrams that I show you. So reduction always occurs at the cathode, oxidation always occurs at the anode. However, in the case of discharge, the cathode is positive, anode is negative. In recharge, is the opposite. And if you reverse the discharge reduction, you get the recharge oxidation and vice versa. So that's that. I think if you don't want to use the reverse arrow, at least remember the polarities or write it out really quickly, let's say before you do the exam, so you can quickly tell. If I say determine the reaction at the negative electrode recharge, you know exactly that I'm talking about reduction. Okay, one last thing is the voltage required for recharge. This is very similar to electrolysis. The voltage required for recharge must be higher than the voltage produced from discharge to account for energy loss in the wire. So let's say if the cell, or if the battery in the case of the lead acid, produces 12 volt, you need more than 12 volt of it to recharge the cell. That's it for this video.